Hello, how are you? I'm going to try to do the class today. Okay. Sorry for these problems. So now pay attention. We're going to start working about. I don't know if you can see me. Okay, but this is not important now. Okay. Okay. So try to keep clean the chat, please. And now, please, don't chat now. Okay. We need time, and we need to go over our theme. And now, please go to your notes, and you have there here in your exercise part an exercise about electromagnetism, and this is a very interesting theme because all devices you have around you are based on electromagnetism, that is the relationship between electricity and magnetism. And in short, this is the same as if we say you have electricity, you can create a magnet. But if you have a magnet, you can create electricity. This is the theme, and this is something that is passionate. And you have here a text, and below you have kind of exercise, true false exercise. We're going to correct it. You sent it to me the other day, but some of them didn't notice that to do it properly, especially some of these sentence that are at the bottom, you need to go to your text part, okay, to your text part. And now you have number one, magnetism wasn't discovered until the 20th century, and this, as you can see, is clearly false. Okay, because magnetism is something that people is being going around it. Okay, even when they didn't know the reason why, there were some facts that happened around them. But magnetism was discovered very soon in the history of humankind. So this first sentence is false, clearly false. Number two, somebody already in the 17th century guessed that the Earth was a magnet, and you have to go here, 17th century, and William Gilbert proposes that Earth is a giant magnet. Okay, this is very interesting. We're talking about the Spanish Golden Age. Okay, when in Spain many people were very famous because they were great poets. They were able to compose beautiful novels. But in other places, especially in England, people were worried about science. Science, not in Spain. Okay, unfortunately. So this second sentence is true. Number three, the first scientist that found a connection between electricity and magnetism was Örsted, and this is true. This is true, and we're going to see a video clip about that, because Örsted was a scientist that was experimenting with electricity, and carelessly he let a compass by the cable, by the wire. Okay, and he noticed that the compass was deflected depending on the place that he put the compass. You know that the compass is a magnetic needle that always points to the north. To the north. But in this case, when you put a compass by a wire with electricity, this electricity is able to deflect the compass. So the first person that noticed that was Örsted, and this is true. So number three is true. Number four, in Europe, navigators used compasses in the Middle Ages, and that's true. In the Middle Ages, even before, I'd say, even before. So very good. So this is true. Number five, the latest discovery about magnetism took place in the 20th century, and you have here Goldsmith and Uhlenbeck show how magnetic properties of materials result from the spinning motion of electrons inside them. That's true as well. Very good. It's number number 6. It was in the 19th century that scientists saw that magnetism had a force that had to be studied. This is clearly true. Clearly true. Good. So number 7, Ampere discovered the electron, but he named it differently. So you don't have this information here. You have to go back to your text part, and we are going to go back to this part in this afternoon. So, but this is true, okay? He discovered the electron, but he named it another different, okay? He named it the electrodynamic molecule or particle, okay? He didn't name it electron, okay? But he discovered it, Ampère, a French scientist. Very important in electricity, in many other fields of science. So number 8, we owe what we study about electromagnetism to Maxwell, okay, and that's true, because there were Örsted, Ampère, Faraday. They were the first scientists that discover the relationship between electricity and magnetism, but only Maxwell was able to put all this knowledge in mathematical forms. Maxwell, very good. In the number 9, Faraday invented the radio. This is not true. We need to go to Marconi, to other people. Finally, Faraday invented the dynamo, a kind of simple electric motor, and that's true. Now please go to your text part, and you have here and below, and below here, this part, the same thing, okay, the same thing. So this is the important thing. Electromagnetism is the connection between magnetism and electricity. Electricity, magnetism. Okay. Attention. Electricity can produce temporary magnets. So you have a coil of wire, and you have something that is made of metal, okay, inside it, and this coil of wire is attached to the electric current. You can turn this metal into a magnet, a temporary magnet. Okay, this is a letter opener, and you can turn this because this is made of iron. Remember, a magnetic material, into a temporary magnet with a north and a south pole. So this is the way to create magnets, temporary magnets that are called electromagnets with a north and a south pole. This is interesting. And then the other ground, magnets. Imagine you have a magnet. Magnets can induce electricity, can produce electricity. And all around us is powered by electricity. But most of our devices that are surrounding us are based on electromagnetism, on electromagnets. And you have here 4 people that you need to know about them. So one of them is the first one, Hans Christian Ørsted, that noticed that a compass needle could be deflected from north when the electric current was switched on and off. And he discovered the relationship between electricity and magnetism, but he couldn't come with any explanation about it. And this is what you are going to see now. This is a video clip about the Öersted experimentation. So be attentive.
In 1820, Danish physicist and chemist Hans Christian Ørsted was setting up materials for a lecture. His materials included an early kind of battery called a voltaic pile, constructed of copper and zinc plates in a
This is a battery, and these are wires. Okay, it's a battery, and these are wires. This is the experiment that Örsted did.
dilute acid solution and a wire held in place here by a set of clamps. Örsted and other scientists of his day knew that when a wire was connected between the positive and negative terminals of a battery, electricity would flow through that wire. Electrons actually move from negative to positive. However, the convention is to think of electrical currents as moving from positive to negative. So that's how we'll show it.
So pay attention. So electrons move from the negative to the positive pole. So you understand? But we have a convention that is the other way around. This is important. We say that electrons go to the positive to the negative, but this is not true. This is a convention. This is a convention, but this is not true. Why? Because if electrons are negatively charged, they have to go to the positive pole, to the north pole. But the important thing is not that. Pay attention now.
But here, using red particles. Back then, scientists still had much to learn.
This is the compass, okay? And the compass is pointing to the north in this moment, okay? In this place, it's pointing to the north. The north is in this position, okay? But now look what happens when the compass is put by the wire.
About electricity. Preparing for his lecture, Örsted made a very important discovery about the phenomenon, quite accidentally. Among Örsted's scientific paraphernalia was a compass. Its needle, of course, pointed north in alignment with the Earth's magnetic field. Örsted happened to place the compass near his battery and was startled to notice that.
Can you see? Can you see? This is the north. This is the north. But when the compass is put here, remember that the compass is a magnetic needle, magnetized needle. So the needle is deflected. The
compass needle moved. As Örsted deduced, this happened because the wire produced a magnetic field around it when it carried a current. If there is no current in the wire, the needle reverts to the alignment with the Earth's
and when you put here, when you open the circuit, so there is no electricity, so the needle goes back to the right position.
Magnetic field. As it turns out, an electric current, made up of moving charged particles, produces a magnetic field that circles around the moving current, as shown by these blue lines. If you reverse the direction of the current, then the magnetic field around the wire moves in the opposite direction, and the needle on the compass flips to reflect the change in field.
You see?
If you move the compass to a new spot near the wire, the needle will realign with the direction of the magnetic field in that particular location. Örsted's accidental discovery was solid evidence that electricity and magnetism were related phenomena. The announcement of his findings incited a tremendous outbreak of research in the nascent field of electromagnetics in the early 1820s.
So very good. This is the Örsted experiment. He was able to notice the relationship between electricity and magnetism, but he couldn't come with any satisfactory explanation for it. Okay, and now we have another person, and this is the French scientist André-Marie Ampère. Okay, André-Marie Ampère found that electric currents along wires can attract or repel each other. So you had to think about two different wires, two different circuits, and the wires are close to each other, and depending on each circuit, these cables, these wires, are able to attract or repel each other. Okay, this was that Ampere was able to discover, and he described the particle that he called the electrodynamic molecule, which could generate electric current. But this electrodynamic molecule is what today is known as the electron. And I'd like you to watch to the following clip. We're going to see just a little part about it. This is a very long video clip, but we only...
Orsted's experiment. In 1820, Hans Christian Orsted performed a simple experiment and discovered...
Sorry, this is not what I want you to... This is something more about Öersted, and what I looking for is this one. This is the clip about Ampere. Pay attention.
It was the autumn of 1820. Hans Christian Öersted had just discovered the connection between electricity and magnetism. Meanwhile, a French physicist named André-Marie Ampère was experimenting with some wires, trying to learn more about the connection between currents and the magnetic fields they create. He took two parallel wires and ran a current through both of them in the same direction.
And you see? You have two different circuits, okay? And you have this wire that belongs to a circuit, and this belongs to another different. You put them this way, they are able to attract each other. That was Ampère discovered.
Direction, and the wires attracted each other. And when he ran a current through both wires in the opposite directions, the wires repelled each other. Studying the strange force between the wires led Ampère to discover one of the most fundamental laws of electromagnetism, what we now call Ampere's law. And that's not the only weird thing that current-carrying wires do. If you wrap a current-carrying wire into a coil, the inside of the coil...
Pay attention now, this is important. Okay, this is a circuit. Okay, positive, the negative pole, and this is the coil of wire, and inside there is an electric field. Now look, we're going to put inside this coil a metal bar, and this metal bar is going to be turned into a magnet, a temporary magnet. Pay attention.
Acts like a magnet. There's a north pole at one end of the coil and a south pole at the other. And if you put a loop of current-carrying wire in a magnetic field, it'll turn. Ampere's law lets you calculate the strength of the currents and magnetic fields in all these situations. This also helps to explain how motors work. So first, those two parallel wires. Why do they attract and repel each other? It's easier to see why the two wires act the way they do if you look at one wire first. Like we talked about in our last episode, the current running through a wire generates a magnetic field. So let's say you have a long straight wire with a current running through it. The current will create a magnetic field circling the wire. That magnetic field decreases the further you are from...
This is the magnetic field, okay? Okay, this is a magnetic field and an electric field. Okay, so the closer to the cable, the stronger. Okay.
The wire. If you draw a circle that's say 1 centimeter from the wire, the magnetic field along the circle will have a set strength. Ampère realized that the stronger the current is that's running through the wire, the stronger the magnetic field would be along that circle. That's the basic logic behind Ampere's law. But this is physics, and in physics we tend to express relationships in terms of equations. The equation for Ampère.
So we're not to watch the equations. So in the future, I think that you were able to do it. Now, go to the next scientist. In this case, we're talking about Michael Faraday. And he discovered that electricity could be made by moving a magnet inside a wire coil. So pay attention. We are used to see that electricity only happens when we put a cable. We plug a cable into a socket. But electricity can be produced with just a magnet. You move a magnet, you can produce electricity. This is called an induced electricity. And Michael Faraday was the scientist that discovered that all our devices, your mobile phones, your computers, your fridge, all our devices are based on what Michael Faraday discovered, on electromagnets. So these would eventually become the electric motor. Faraday's experiments paved the way for changing mechanical energy into electrical energy. And you have here another video clip about Michael Faraday, just 2 or 3 minutes.
Newton, Lavoisier, Darwin. What do they all have in common? All these science geniuses came from wealthy families. But Faraday, a working-class child, not only joined that highly select private club, but also unravelled one of science's all-time greatest mysteries. Born in a humble family, Michael Faraday experienced the hardships of the 19th century English society. Working at a bookshop, he taught himself science through the books he read. He also managed to go to Humphrey Davy's lectures about chemistry.
This is Humphrey Davis, okay? A very famous scientist, Humphrey Davis. Humphrey Davis and Faraday went to Humphrey Davis lectures. He got very interested in what he was saying.
In electricity and was dazzled by them. He wrote a book that summarized the lectures. Davy was amazed and took Faraday on as a lab assistant who assisted him on his trips, where he met other scientists. That's how he learnt about magnetism and the ongoing discussion about its relationship with electricity. Scientists imagined them as different fluids moving through the air and wires with no relation between them, until Örsted discovered that current passing through a wire moved a nearby compass. Electricity and magnetism were then connected.
This is the Örsted experiment. Okay? Örsted experiment.
Somehow. By this time, Davy had suffered an accident, and then Faraday could do his own experiments. Trying to explain Örsted's results, Faraday thought that, the same as vibrations of sound fly through the air, making objects vibrate, then maybe electricity wasn't a fluid, but a sort of vibration carried through the air as magnetism. So he designed an experiment.
Attention, this is a coil of wire that is wrapped around a bar of metal. Okay, this is a normal bar of metal. And this bar of metal is going to become a magnet.
He took an iron ring, isolated it, and wound 2 coils on the extremes. Connecting one to a battery, he saw that switching it produced an electrical current on the other. Faraday deduced that the coil emitted magnetic vibrations that travelled through the ring, inducing electricity on the second wire. But if changing the magnetic vibrations caused the second current, why not use a magnet directly?
Now pay attention. Now you have here a magnet. This is a magnet, and he's going to put the magnet into this coil of wire, and he's going to move this magnet up and down, and because of that he's going to generate electric current.
He moved a magnet through the second coil and it generated electric current. Faraday discovered magnetic induction, and in 1831, using it, constructed the first dynamo ever, a way to...
This is a dynamo. This is the dynamo. Dynamo is something you can see in many bikes. When you move your legs, when you are advancing, when you are running, you are moving your legs. There are some bikes with a dynamo, and this dynamo is able to shine a light that are placed in the front of the handbar.
Convert movement into electricity. This popularized electricity, democratizing its use.
This is the dynamo. This is the dynamo. This is the light. Okay, and the dynamo is producing electricity. Why? Because inside the dynamo there is a magnet. When you are moving your pedals, you're moving your legs. This wheel is moving, and the magnet is moving, and this is inducing an electric current that goes up to the lights, and it shines.
use and making it possible to be available everywhere.
And this is true for the dynamo, this is true for this windmill, this is true for our electric cars. Very good, very good. So now let's go to our text. And the last man, the man that was able to turn all these discoveries into science, real science, with mathematical equations, was James Clerk Maxwell, and he described scientifically the electromagnetism. Maxwell's work included 20 famous mathematical equations. This is Maxwell. And below you have here the principles of electromagnetism that are reversible. So, an electric current in a wire generates a magnetic field. In this magnetic field induces an electric current, and the other way around. Okay, this is a cycle. Very good. Now you have here some exercises. You don't have to do these exercises. You have to think about them. The exercise number 18 and number 19 are exercises you can do at home, but you don't have to do them now. You have something more to do today about static electricity. It's good. I think this is our class today, and I don't know, you have some questions for me. You have any questions for me? Sorry for the technical problems. Sorry. Okay, I think it's time to finish the broadcasting. We'll try to improve for next time. So, see you.